72. From the form of the expression for capital A in equation 20, namely the flux of energy due to the stress, we may derive the expression for the electromagnetic stress itself. If the stress were of the irrotational type considered in works on elasticity, we could do this by means of the formula 10 in section 68. But for a stress of the most general type, the corresponding formula is capital A equals negative Q sub P. That is equation 28. Here Q sub P is the stress vector conjugate to P. These are identically the same when the stress is irrotational. This gives Q sub N equals DEN plus BHN minus N multiplied by open parentheses U plus T close parentheses. That is equation 29, from which we obtain P sub N by merely exchanging E and D and H and B. Thus, P sub N equals EDN plus HBN minus N multiplied by open parenthesis, U plus T, close parenthesis. That is equation 30. This is the stress vector for any plane defined by N, a unit vector normal to the plane. But it is only in iotropic bodies that we have to distinguish between the directions of a force and of the corresponding flux. Putting these on one side and considering only ordinary isotropy, the interpretation is simple enough. It will be observed that the electromagnetic stress equation 30 divides into an electric stress EDN minus N multiplied by 1/2 ED. That is equation 31, and a magnetic stress HBN minus N multiplied by 1/2 HB. That is equation 32. To find their meaning, take N in turns parallel to and perpendicular to the force E, or to D, since its direction is the same. In the first case, the stress equation 31 becomes N multiplied by open parenthesis ED minus 1/2 ED close parenthesis equals N dot ED equals NU, indicating a tension parallel to the electric force of amount U per unit area. In the second case, when N is perpendicular to E, we have DN equals 0, so that the stress is negative NU. That is a pressure of amount U. This applies to any direction perpendicular to E, so that the electric stress consists of a tension U parallel to the electric force, combined with an equal lateral pressure. Similarly, the magnetic stress consists of a tension T parallel to the magnetic force, combined with an equal lateral pressure. It will also be found that the tensor of the electric stress vector is always U, and that of the magnetic stress vector is always T. The following construction figure 5 is also useful. Let ABC be the plane on which the electric stress is required, Bn the unit normal, Be the electric force, Bp the stress. Then N, E, and P are in the same plane, and the angle between N and E equals that between E and P. Or the same operation which turns N to E also turns E to P, except as regards the tensor of P. To show the transition from a tension to an equal pressure, imagine the plane ABC to be turned round, and with it the normal N. Of course, E remains fixed, being the electric force at the point B. Start with coincidence of N and E. Then P also coincides with them and represents a normal pull on the surface ABC. As N and E separate, so do E and P equally, so that when E makes an angle of 45 degrees with N, the normal pull is turned into a tangential pull, or a shearing stress, P being now at right angles to N. Further increase in the angle E makes with N brings BP to the other side of BC, and when E is at right angles to N, we have P and N in the same line, but oppositely directed. That is, the tension has become converted into an equal pressure. Paragraph 73. We may now consider the practical meaning of the stress whose relation to the electric and magnetic forces has, under certain suppositions, been formalized. Go back to the foundation of electromagnetic theory, namely the mechanical forces experienced by electrically charged bodies, by conductors supporting currents, and by magnets, intrinsic or induced. It is by observation of these forces in the first place, followed by the induction of the laws they obey, and then, by deductive work, that the carving out of space into tubes of force follows. And now, further, we see that the localization of the stored energies, according to the square of the electric and magnetic force respectively, combined with the two circuital laws, leads definitely to a stress existing in the electromagnetic field, which is the natural concomitant of the stored energy, and which is the immediate cause of the mechanical forces observed in certain cases. But the theory of the stress goes so far beyond experimental knowledge in some respects, although agreeing with it in others, that we could only expect it to be true if the theoretical foundations were also rigidly true in all respects. Such is not the case, however. To begin with, the way of expressing the action of ordinary matter merely by altering the values of the two other constants, and by a fresh property, that of conductivity, is extremely bald. It is indeed surprising what a variety of phenomena is explained by so crude a method. The objection is sometimes made against some modern theoretical developments that they are complicated. Considered as an argument, the objection is valueless and only worthy of superficial minds. Whatever do they expect? Do they not know that experimental knowledge, even as at present existent, shows that the theory of electromagnetism, when matter is present, must, to be comprehensive, be something far more instead of less complicated than theory as now developed? The latter is, as it were, merely a rough sketch of a most elaborate subject, only small parts of which can be seen at one time. In the next place, even if we take the stated influence of matter on the ether as sufficient for the purposes of a rough sketch, the theory must be used with caution. Why this should be so will be apparent on examining the manner in which the stress has been obtained from the circuital laws. If we investigate these abstracts statically, and, starting from certain mechanical forces regarded as known, endeavor to arrive at a stress which shall explain those forces, we shall find the problem essentially indeterminate. All sorts of stress functions may be made up which are precisely equivalent in their effects in the gross, that is, as regards translating or rotating solid bodies placed in an electric or magnetic field. To remove this indeterminateness, a dynamical method must be adopted, wherein what goes on in the unit volume whilst its electric and magnetic states are changing, and the matter concerned is itself in motion, are considered. If our system of connections is dynamically complete and consistent and is such that the flux of energy can be traced, then a determinate stress comes out, as we have found. The method is, at any rate, a correct one. However, the results may require to be modified by alterations in the data. Besides that, the distribution of energy, electric and magnetic, in bodies is in some cases open to question. And a really speculative datum is that concerning the motion of the ether as controlled by the motion of matter. Now, this datum appears to be one which is essential to the dynamical method. The only alternative is the statical and quite indeterminate method. Our attitude towards the general application of the special form of the stress theory obtained should therefore be one of scientific skepticism. This should, however, be carefully distinguished from an obstinate prejudice founded upon ignorance, such as is displayed by some anti-Maxwellians, even towards parts of Maxwell's theory which have received experimental demonstration. The stress theory can, nevertheless, sometimes be received with considerable confidence, if not absolute certainty. The simplest case is that of ordinary electrostatics. The electrostatic stress in air. Let there be no magnetic force at all, and the electric force be quite steady, and the medium be at rest, and there be no impressed forces. These limitations bring the circuital laws down to divergence of E equals 0, that is equation 1, and curl of E equals 0, that is equation 2. That is, there must be no conduction current anywhere, and the voltage in any circuit must be 0. The first condition, divergence of E equals 0, implies that there is no electric force in conductors. We may therefore divide space into conducting and non-conducting regions, and our electric field is entirely confined to the latter. The second condition, curl of E equals 0, implies tangential continuity of E at the boundary of the non-conductor, so that as there is no E in the other or conducting side, there must be no tangential E on the non-conducting side. The lines of force, therefore, terminate perpendicularly on the conducting matter. Whether the conductors are also dielectrics or not is quite immaterial. The displacement also terminates normally on the conducting surface in the usual case of isotropy. Thus D, the tensor of D, measures the surface density of electrification, when the positive direction of D is from the conductor to the insulator. But in general, it is the normal component of D, that is dN, where n is the unit normal vector that measures the density of the electrification. Besides this, there may be interior electrification of the non-conductor, its volume density being measured by the divergence of the displacement. The arrangement of the electric force so that the circuital voltage shall be 0 throughout the non-conductor and give the proper internal electrification, and the charges on the conductors is uniquely determinate. We have thus the ordinary case of a number of charged conductors in air, with the difference that the air, or parts thereof, may be replaced by matter of different permittivity. It is also to be noted that one non-conducting region, which is entirely separated from another by conducting matter, may be taken by itself, and all the rest ignored. Now, first, without replacing the air by matter of different permittivity, we see that there are two entirely different ways of considering the mutual actions of the conductors. The old way is analogous to Newton's way of expressing the fact of gravitation. We may say that any element of electrification ρ repels any other ρ prime with a force ρ prime over 4 pi epsilon r squared, if r be the distance between the two charges, and that the resultant of all such forces makes up the real force. In the other way, appropriate to the philosophy of Faraday as developed by Maxwell, these forces acting at a distance are mathematical abstractions only, and have no real existence. What is real is a stress in the electric field of a peculiar nature, being a tension of amount U parallel to E, combined with an equal lateral pressure. And it is the action of this stress that causes the electrified conductors to move, or strains them, according to the way they are supported, when by constraints they cannot appreciably move. Since the electric force is normal to the conducting surfaces, the stress vector is entirely a normal pull of amount U per unit area, and the motions or tendencies to move the conductors are perfectly accounted for by this pull. They do not move because of electrical forces acting at a distance across the air, but because they are subjected to moving force on the spot by the stress terminating upon them. Thus, a charged soap bubble is subjected to an external radial tension and therefore expands, and so no doubt does a charged metal sphere to some small extent. The parallel plates of a condenser are pulled together. When they are very large compared with their distance apart, the force on either is 1/2 ED multiplied by the area, or 1/2 E multiplied by the charge. Here E is the transverse voltage divided by the distance between the plates, so that if the plates be connected to a constant source of voltage, the attraction varies inversely as the square of the distance between them. Whereas, if the plates be insulated and their charge is constant, the attraction is the same at any distance sufficiently small compared with the size of the plates. But by sufficiently separating the plates, or by using smaller plates, the displacement, which was formerly almost entirely between them, will spread out and will terminate in appreciable amount upon the sides remote from one another. By the pull on the remote sides thus produced, the attraction will be lessened, and the further the plates are separated, the more displacement goes to their backs, and the less is the attraction. When the distance is great enough, it tends to be simply the attraction between 2-point charges. Thus, the attraction between two distant, oppositely charged conducting spheres, which varies closely as the inverse square of the distance, depends entirely upon the slight departure from uniformity of distribution of the electrification over their surfaces, whereby the normal pull on either is made a little greater on the side next to the other than on the remote side. Also, the inverse square law itself, which is exactly true for point charges, is merely the ultimate limit of this operation. Some attacks have been made on the law of inverse squares, especially in its magnetic aspect. But these attacks appear to have been founded upon misapprehension. The law is true and always will be. Paragraph 75. The moving force on electrification, bodily and superficial harmonization. In the above electrostatic application of the stress, it will be observed that the tension alone comes into play, at least explicitly, owing to the tubes of displacement terminating perpendicular on the conductors. Thus, each tube may be compared with a rope in a state of tension, pulling whatever its ends may be attached to. But the lateral pressure is needed to keep the medium itself in equilibrium, so that the only places where translational force arises from the stress is where there is electrification. The mechanical force is F equals E divergence D minus EP, equation 3, per unit volume. This is the force on volume electrification and is the result of the differential action of the stress round about the electrification, as in the case of the inverse square law between point charges lately mentioned. The corresponding surface force is F equals 1/2 EdN minus NU, equation 4, per unit area. Now here dN is the surface equivalent of divergence D. So there is at first sight a discrepancy between the expressions for the force per unit volume equation 3 and per unit area equation 4 on bodily and surface electrification. How the coefficient 1/2 comes in may be seen by taking the limiting form of the previous expression. Let there be a thin skin of electrification of amount sigma per unit area, E falling off from E outside to 0 inside the skin. Evidently, the mean E is 1/2 E, so that the total force on unit area of the skin obtained by summation of the forces on the volume electrification in the skin is not sigma E, but 1/2 sigma E. This is merely a mathematical harmonization. From the point of view of the stress, the difficulty does not present itself. The harmonization is simply evident when the layer is of uniform density, for the electric force will then fall off in intensity uniformly. It might, however, be suspected that perhaps the result would not come out quite the same if we assumed any other law of distribution and kept to it in proceeding to the limit by making the skin infinitely thin. But a cursory examination will show that it is all right. For if E is the electric force within the layer, the electrification density will be CdE over dx, and the translational force will be Ce multiplied by dE over dx per unit volume, if x is measured perpendicularly to the skin surfaces. Integrate through the skin, and the result is F equals 1/2 CE1 squared minus 1/2 CE2 squared equals U1 minus U2, where the suffixes refer to the value just outside the skin on two sides. In the present case, the second term U2 is 0 within the conductor, so that the result is the single normal pull of the tension on the non-conducting side. Paragraph 76. In this connection, the old question of the depth of the layer of electrification on a conducting surface crops up. Has it any depth at all, and if so, how much? The question is not so superficial as it looks, and the answer thereto lies in the application thereof. If a powerful mental microscope be applied to magnify the molecules and produce evident heterogeneity, the surface of a conductor would become indefinite. And unless the molecules were found to be very closely packed, that the displacement in the ether outside the conductor would not terminate entirely upon those molecules which happen to be most superficially situated, but that a portion of the displacement would go deeper and insensible amount reach molecules beneath the first set, and an insensible amount might penetrate through many layers. Thus, in a molecular theory, the depth of the layer of electrification has meaning and could be roughly estimated, but the case is entirely different in a theory which deliberately ignores molecules and assumes continuity of structure. A conductor is then a conductor all through and not a heterogeneous mixture, and the surface of a conductor is an unbroken surface. The electrification on it is therefore surface electrification and has no depth. For it to be otherwise is simply to make nonsense. It is desirable to be consistent in working out a theory for the sake of distinctness of ideas. If, then, we wish to give depth to surface electrification and still keep in harmony with Maxwell's theory, we must change our way of regarding a conductor and bring in heterogeneity. Each view is true in its own way, but as in the mathematical theory, continuity of structure is tacitly assumed, we have a simultaneous evanescence of one dimension in the distribution of electrification. The same question occurs in another form in the estimation of bodily electrification, when the meaning of volume density of electrification is considered. When air is electrified, it is probable that the electrification is carried upon the foreign particles suspended in the air, and it may be partly upon the air molecules themselves. In either case, it is ultimately surface electrification and quite discontinuous. But merely for the sake of facility of working, it is desirable to ignore all the discontinuity and assume a continuous and practically equivalent distribution of bodily electrification. Thus, as previously we saw surface density to be a kind of volume density, so now we see that volume density is a kind of surface density. When, therefore, we say that the translational force per unit volume is E rho, where E is the electric force and rho the volume density of electrification, we really mean that E rho is the average obtained by summation of the translational forces on the multitudinous electrified particles, every one of these forces being itself a differential effect, as before seen, namely the resultant of the unequal pulls on different parts of a particle exerted by the electric stress. As ether has some of the properties of matter, and as electrification is found in association with matter, it is possible, however improbable, that ether itself may become electrified. But of this nothing is known. Nor, more importantly, is it understood why the electric stress appears to act differently on positively and on negatively electrified matter. But if we begin to talk about what is not understood, we enter illimitable regions. Men who are engaged in expounding practical problems sometimes make the boast that they take and discuss things as they are, not as they might be. There is a sound, specious plausibility here, which is grateful and comforting. But, as a matter of plain fact, questions of physics never are theorized upon as they are, but always as they might be. It is a necessity to limit the field of inquiry, for to take things as they are, or as they seem to be, would lead at once to a complete tangle. For the problem as it presents itself in reality, there is always substituted a far simpler one, containing certain features of the real one emphasized, as it were, and others altogether omitted. The juveniles who take things as they are do not do it. They only think so. They may strain out a few gnats successfully, but swallow quite unawares all the camels in Arabia. But the principle and practice of limitation and substitution is the same all over. In politics, for instance, where a fictitious British constitution does brave duty as a scarecrow, and in other useful ways. Paragraph 77. Electric field disturbed by foreign body. Effect of a spherical nonconductor. To further exemplify the significance of the electric stress, let us introduce a foreign body into a stationary electric field. The field will be disturbed by its introduction and will settle down to a new state. The change depending upon the nature of the foreign body, whether conducting or non-conducting in substance or superficially, and upon whether it has a charge itself or contains any other source of displacement. If it be a good conductor, either charged or uncharged, the final state, reached very quickly, will be such that the displacement will terminate normally upon its surface, thus reproducing the previous case, sections 74 to 76. But if it be a non-conductor, the result is somewhat different. If superficially conducting, we may indeed have an ultimate electrification of the surface, so as to come wholly or partly under the same case. But if there be no superficial or internal conduction, our only issue is that the stress must elapse for it to become fully effective. What we do is simply to replace the dielectric air in a certain region by another dielectric of different permittivity, usually greater. Then supposing the external field to be due to charges upon insulated conductors or to internal electrification in the air, no change will occur in their amounts, but there will be merely an alteration in the distribution of the electrification on the conductors, like current caused by the displacement becoming denser within the foreign body than before, or less dense if its permittivity can be less than that of the air. The intrinsic electrification of the body itself, if any, must also be allowed for, but should it have none previously, it will remain unelectrified when introduced into the field, and the displacement will pass freely through it and out again in a solenoidal manner. This is expressed by the surface condition d1n1 plus d2n2 equals 0, where d1 and d2 are the displacements in the air and foreign body respectively at their interface, and n1, n2 are the unit normals from the interface to the two media. The only quite simple case, excepting that of infinite plane sheets, is that of a sphere of uniform permittivity brought into a previously uniform field. The ultimate displacement in the sphere is then parallel to the original displacement in the air. It may vary between 0 and 3 times the original displacement, as the permittivity of the sphere varies from 0 up to infinity. It is certainly a little surprising that the ultimate displacement with infinite permittivity should be only 3 times the original, and it is not much less when the permittivity is only 10 times that of the air. Whilst on the other hand, the zero displacement when the permittivity is 0, a quite ideal case, is obvious enough because the displacement never enters the sphere at all, but goes round it. The original uniform field may be conveniently treated as between the parallel plates of a very large air condenser. There is, however, a double action taking place. When the transverse voltage of the condenser is maintained constant by connection with a suitable source, the insertion of the foreign body, which increases or reduces the permittance of the condenser, will increase or reduce the displacement under the action of the constant source, besides concentrating or diffusing the lines of displacement. The increase of permittivity also increases the stored energy when the transverse voltage is constant, but reduces it when the charges are constant. Now, since the electric force does not terminate on the boundary of the foreign body, but extends all through it, so does the electric stress. So far, however, as the resultant force and torque on the body when solid is concerned, we may ignore the internal stress altogether and consider only the external, or stress in the air. This is a particular case of a somewhat important wide property in abstract dynamics, which we may state separately thus. Paragraph 78. Dynamical principle. Any stress self-equilibrating. The resultant force and torque due to any stress in any region is 0, or any stress in any region forms a self-equilibrating system. Imagine any distribution of stress to exist in a region A and to terminate abruptly on its boundary. Or equivalently, imagine a piece of a stressed solid to be removed from its place without altering the stress. The stress variation, when estimated in a certain way, constitutes mechanical force tending to move the body. This will be, in the case of an ordinary irrotational stress, entirely translational force. But there are two kinds. First, there is internal force, reckoned per unit volume, due to the continuous variation of the stress in the body. Next, there is superficial force, reckoned per unit area, due to the abrupt cessation of the stress. This surface traction is represented simply by the stress vector itself, acting on the inner side of the surface of the body. Now, the resultant effect of these two forces, over the surface and throughout the volume of the solid respectively, intending to translate and rotate it, is zero. Or, in other words, the forces and torque equivalent to the surface force are the negatives of those due to the internal force. If it were otherwise, the differential action would cause indefinite increase in the translational and rotational energy to arise out of the internal mutual forces only. If the stress be of the rotational type, there will be an internal torque per unit volume, as well as a translational force. Still, however, the resultant force and torque due to the surface tractions will cancel those due to the internal forces and torques. In case there be any difficulty in conceiving the traction exerted on the surface of a body by the stress within itself, we may replace the sudden cessation of the stress by a gradual cessation through a thin skin. The solid is then under the influence of continuous bodily force only, and torque also, if the stress be rotational, conveniently divisible into the internal force all over and the force in the skin. Otherwise, it is the same. Now put the solid piece back into its place again. Since its own stress balances itself, we see that whatever the force on the piece may be, it must be statically equivalent to the action upon its boundary of the external stress only, constituting an external surface traction. There need be no connection between the external and the internal stress. The latter may be anything we like, so far as the resultant force and torque on the piece are concerned. The difference will arise in the strains produced or in the relative internal motions when for one stress another is substituted.